Floor is yours.
I would like to offer a warm welcome to tonight's presenter, Dr. Andrew Luhmann, the Assistant Professor of Geology at Wheaton College. After completing graduate school, Andrew conducted research as a postdoctoral researcher for 4 years in the Department of Earth Sciences at the University of Minnesota in Minneapolis. He spent the following 3 years as an assistant professor of hydrology at the Department of Earth and Environmental Science at the New Mexico Institute of Mining and Technology. His research generally involves the fields of hydrogeology and geochemistry. His current research projects explore geophysical responses in karst aquifers and geologic carbon sequestration environments. I'll say that 10 times real fast. He previously served as an associate editor of the Hydrogeology Journal and primary representative of the Joint Technical Program Committee for Geological Society of American Karst Division. And I didn't figure out what the acronym is on that one. That's a really long one.
Yeah.
Andrew received his PhD in geology from the University of Minnesota. And with that, I'm going to stop talking and start taking notes. Andrew, the floor is yours.
All right. Thanks very much, Catherine, for that introduction. Let me share my screen. And it's a little smaller. All right. Well, again, it's really good to be with all of you this evening. So thanks for inviting me to join your group. I do a lot of work in karst aquifers, and I'll explain what that is in a little bit more detail here real soon. But generally, we have conduits or caves where we get a lot of groundwater flow in the subsurface. And up in the upper right corner here on this image, I'm showing some seismic data that was collected from a seismometer that was right at the Earth's surface. And one of the questions we're after is, can we actually make use of this seismic information, recording various kinds of processes as water's flowing through caves and other features in the subsurface? Can we make use of that data to infer anything about the conduit network and characteristics of the aquifer that exists in the subsurface? But before I begin, I need to acknowledge a lot of people who have made this project possible. So I myself am not a geophysicist. I'm not a seismologist. That's primarily Sue Billick. So she's a professor of geophysics at New Mexico Tech. I initially went to her and kind of proposed this idea, and she said, yeah, let's try it. And so we've been trying it here for the last few years. So I need to acknowledge her. Jacob Gokenauer is a PhD student at New Mexico Tech. Han-Bir Wu is a postdoc at New Mexico Tech. These three have contributed a lot to this project. Also, some other colleagues at New Mexico Tech, Ronnie Groppentine at the University of Alaska Fairbanks. Worked closely with John Martin, Madison Flint, and a whole host of other colleagues at the University of Florida, Matt Covington at the University of Arkansas. There's been several students at Wheaton who have been involved in this project, and in particular, Ethan, Julia, Benjamin, Ethan, Isaac, and Donovan, and Samuel Dunbar have all helped with a museum exhibit that I'm going to show you here in just a few moments. And then there's some colleagues, including my PhD advisor, some colleagues up in Minnesota. All of the seismometers that we use were provided by the Iris Pascal Instrument Center in New Mexico. And then at the very end of the talk, I'm going to talk about some work that we've done in Olino and River Rise Preserve State Parks. So all the staff there was really helpful in terms of completing this project. And then finally, funding was provided by the Wheaton College Summer Research Programs. That's funded some of our students to work on research. And then this grant was primarily funded by the National Science Foundation. All right, so in this talk, there'll be three main parts. First of all, I'm going to give you a brief introduction into karst hydrogeology. And then I'm going to tell you about some new opportunities for how we can make use of geophysical tools to learn about caves and other features in these systems. Then the second part is the Earth burps part of the talk. We're going to look at whether these seismometers are able to capture the Earth burping as we're releasing these overpressurized air pockets, and how we can perhaps make use of that to map out caves in the subsurface. And then finally, at the very end, we're going to look at what happens as we raise water levels in the aquifer. We're basically going to look at the tilt of the land surface. And there are instruments that are capable of recording very small tilts. And so we're trying to make use of those as well to try to characterize some of the unknowns in the subsurface. So let's first of all begin with karst hydrogeology. Shown here is one of my favorite images. This is a karst landscape. With a karst landscape, they basically develop in areas where you have soluble rock. And a common rock where this happens is limestone. So where you have limestone, if you have a lot of precipitation, it's probably pretty safe to assume that there's conduits of some size that exist in the subsurface. And so there's a lot of chemical reactions that are relevant. But limestone is CaCO3 that reacts with carbonic acid. There's water, or there's CO2 in water as it falls to the surface, but then as that water infiltrates into soils, it actually picks up a lot more CO2 from microbial processes in soils. So carbonic acid reacts with this limestone, and the net result is you dissolve away the rock. You produce some calcium in the water and some bicarbonate in the water. So below the Earth's surface, you can develop these significant cavities. At the Earth's surface, you can develop sinkholes or things like sinking streams, as is shown on the right. And then some of the largest caves that we see throughout the world are in these kinds of systems. And that's basically because you have big caves where water can move through very quickly. So all of a sudden you have a spring location where water discharges from the rock. Because you have big cavities underground, sometimes you can get these catastrophic sinkholes that develop. And so perhaps some of you remember this when this happened almost a decade ago now at the National Corvette Museum. All of a sudden, the facility just collapsed into this massive sinkhole. Shown here is a picture, or a video rather. And this is one of the field sites that I worked at when I was a graduate student. Normally, there wasn't any water flowing here, but I was monitoring some water flow in another part in a cave passage not too far away. But this was after a massive rainstorm event, and you can see this large flux of water just simply disappearing underground. So obviously you need to have these big cavities underground for this water not to pond on the surface. And so if you go below the surface, you would see something like this. Actually, just kidding, you wouldn't see something like that. You'd see something like this instead. So this is a picture in Tyson Spring Cave in Minnesota. I did a lot of work in here when I was a graduate student. And it's a little difficult to see from the picture, but right in the ceiling, there is a fracture. And so what happens is as the water is moving through this rock, it preferentially wants to pass through that fracture. It's easier to flow through the fracture than the rock matrix. And so as water starts to flow along that fracture, it dissolves along that fracture. And so it repeatedly causes more and more dissolution until eventually you get these passages that are large enough that people can even enter. Obviously, these flow paths are important and water can move very quickly in the subsurface. And then eventually this water can discharge at a spring. So this is a spring not too far away down in the Ozarks in Missouri, but this discharge point connected to cavities that exist below the surface. Karst landscapes are pretty abundant on the Earth's surface. They cover 15.2% of the ice-free land. Is carbonate rock specifically. Generally, we're talking about limestone or else dolostone. Dolostone is very similar to limestone, but there's some magnesium in it as well. It's estimated that about 16.5% of the global population lives on these karst landscapes where you could have some caves that exist below the surface. And because of this, a lot of human civilizations are dependent on groundwater resources from these systems. So these are really important aquifers that provide water to a lot of the global population. The colors here, the dark blue and light blue indicate either continuous or discontinuous carbonate rocks, but you can also develop karst landscapes on evaporite rocks, things like gypsum, so that will readily dissolve, and those are indicated in the pink and the yellow orangish color as well. If you zoom in, here's a map of 48 of the states here in the US. And what this map is showing is the karst landscapes that exist in the US. Generally, the eastern half of the US receives a whole lot more precipitation. So this is a humid environment. And so whenever you have limestone in these humid environments, it's probably safe to assume that you have conduits of some degree that exist below the surface. They may not quite be large enough for humans to enter, but you've probably caused some dissolution to form some caves. The high mountainous areas can also have significant precipitation, so that's indicated by the gray color. The tan indicates arid environments where we have less precipitation. So it's more difficult to develop caves there because there's not a whole lot of water that moves through the system. But in this talk, I'm going to take you to a place in Ontario in Canada. We're going to look at what happened with a contamination issue there that ultimately killed some people. And then we're going to spend most of the time talking about southeastern Minnesota, where we did a little test study. And then finally, we'll come down here to north central Florida. But here we're looking at areas where we have carbonate rock that exists very near the Earth's surface. And so again, when a lot of water flows through these rocks, it readily dissolves in order to form some karst landscapes in the subsurface. Illinois, we have the right rocks. In the northeastern corner, a lot of these rocks are deeply buried by glacial sediments. You can see some carbonate rocks in the northwest corner that aren't really covered by glacial sediments. And then, especially as you get to the southwestern part of Illinois, you can see some karst features. In particular, right around the St. Louis area, you can see some massive sinkholes because there's some pretty significant karst development there. And then you cross the border, Missouri has a ton of karst. You can see that it has a lot of the right kind of rock, and then in these humid conditions, it develops these karst landscapes. So one of the central problems that we have in karst hydrogeology is we can monitor the rain that falls on the karst landscape. We can also monitor at a spring, which is basically integrating all the different flow paths in the aquifer. But in most cases, it's these conduits that are driving most of the flow and the transport of any sort of constituents in the water through the aquifer system. But in most cases, it's a question mark. We have no idea where they're actually located. In fact, when I was a PhD student, there was this massive rainstorm event near one of my field areas in southeastern Minnesota. And there was a large collapsed sinkhole that developed. Shortly after that, some cavers dropped down into the sinkhole, and they started to map out this cave. Here's a person for scale. So this was a cave. They had some idea there was probably something there, but it wasn't until this rainstorm opened up a new sinkhole that they started to see that there's this massive cave in the subsurface. So within the first few months, they had already mapped kilometers of passage in the subsurface. But with these big caves, water can move very quickly through these systems. And the reason why that is an issue is because if you have any sort of contamination spill, it can quickly contaminate the water resources for all of those who live somewhere downstream. And unfortunately, this was a site in Walkerton, Canada. This was a location that ultimately 7 people in the community were killed, and nearly half of the community ultimately became sick. In this case, they became sick because there was a lot of things like E. coli that had contaminated their water supply. And so the community was trying to figure out what contaminated their water supply. They initially had some groundwater specialists come in, and they ran some groundwater models to try to figure out where the contaminant was coming from. And this circle basically just shows the area where they thought some of the contaminants could have come from to ultimately contaminate this well. But when you don't have caves, water generally moves very slowly through the subsurface. Later on, some karst specialists came in, and they did some dye traces where they dumped dye at different locations. And they found that water's moving hundreds of times faster than they thought it was before they considered that there might be some conduits in the area. So one of the things we're after is trying to characterize where these conduits are at, such that we know what potential places will be impacted if there's contaminants that are released at some location. In this case, it ended up being tied to some sort of cattle operation, and there was E. coli, various kinds of bacteria that impacted the water supply. And so people were drinking that water, it wasn't treated properly. And so that's ultimately what killed 7 people and made nearly half of the community sick. All right, so a little bit about karst hydro. Now let's talk a little bit about geophysics as well. And on this slide here, I'm trying to illustrate seismometers with these simple little cartoons. But we basically make use of seismometers in order to record ground motion. And the seismometer nowadays looks a little different, but it's the same kind of principle. You have the instrument that is mounted onto the Earth's surface, and then there's the suspended mass, which is hung by a cable. And so as the land surface starts to move, you are able to monitor for these perturbations. So in this case, it's set up where we're looking at horizontal perturbations, or if we get an earthquake and we get vertical perturbations, we can have another setup where here we're able to record these vertical perturbations. And with the instruments that we were making use of, we were able to keep track of how the land surface is moving both vertically and then also in a north-south orientation and an east-west orientation as well. Traditionally, these seismometers have been used in order to determine things like where an earthquake originated from. And so if some of you have taken an introductory geology class, you've probably done some sort of exercise like this. Here we're looking at 3 seismic records that have been recorded at 3 different stations, which are indicated by the circles here on this map. Here we're showing the arrival of a P wave and the arrival of an S wave. A P wave is the primary wave and it travels the fastest. It's a compressional wave, much like a slinky. An S wave is a shear wave and it travels more slowly. And you can see that we can look at the arrival of the P and the S wave at the seismic station. And we can use that time difference as a way to infer how far that station was away from the earthquake. So in this case, this station was right here, and we know that it occurred at a distance that was 900 kilometers away. And so we can draw a circle with that radius of 900 kilometers and know that the earthquake occurred somewhere along that circle. Then you go to another station. Here you can see that the distance between the arrival of the P and the S waves is even greater. So in this case, this distance would correspond to a distance of 1,800 kilometers. So similarly, we can go to this seismic station, again, a radius of 1,800 kilometers, and we can draw another circle. And you can see with 2 seismic stations, those circles overlap in 2 spots. But if we have a third station and draw another circle, do the same thing, all of a sudden you'll see those 3 circles will only overlap in 1 location. So here we can use these seismic records as a way to infer where these earthquakes ultimately originated from. But we can actually use this seismic data in even more significant ways as well. In this case, what we're doing is we're looking at how seismic waves are propagating through the subsurface. And here, they're basically looking at how that velocity of the P wave is changing as it moves through these different materials. And this can change as it moves through materials of different density or perhaps different temperatures. It can all cause oscillations in these P waves. But in this case, we're looking at this site. On the map of the globe, you can see a white line, and that's basically a cross section. So we're basically slicing the earth like a piece of pie, and then we're going to turn the earth on its side. From this P wave velocity anomaly, we can actually track how the Pacific plate is subducting below Tonga. So we can use how seismic waves propagate through the subsurface as a way to infer the structure that exists in the subsurface. And so similarly in this project, we're trying to do the same. We're trying to see if we can characterize what these karst aquifer systems look like. And I'm not going to show you any images like this today, but we're starting to generate some for our field site down in Florida. Now, one of the things that made me initially think that we should see if we can use seismometers to detect various kinds of processes in karst aquifers was this image that is shown here on this graph. On the y-axis on the left, we're seeing a tremor amplitude. That is a signal that's being recorded by a seismometer. And that is indicated here as a function of time in this black curve. So you can see the tremor gets large here and then it comes back down. Quick question, as I'm moving my mouse, can you see my mouse move on the screen? Yes, all right. So as tremor gets large and then it comes back down. In the blue, we can see a record of water level. This was a seismometer that was located right near a glacier in Alaska. So that's providing the black curve. And then the discharge signal was a USGS gauging station that was monitoring how much water was coming off of the base of the glacier. And they're certainly not at the point where we can use a seismometer to quantitatively tell how much water is flowing. But you can see there's a pretty good relationship. As the seismic signal goes up, so does discharge. And so our thought is maybe we can use these seismic signals as a way to monitor for how water levels are changing in the subsurface. And again, I'm not going to quite show you any of that in this talk, but we're starting to do some of this analysis and we're starting to see something similar. All right, so a little bit about geophysics. And then before I really jump into the research, I'm going to introduce this interactive museum exhibit that we built. This is basically trying to illustrate what we are trying to do in the field. So I'll show you this little museum exhibit, and then we'll look at the data at a couple of field sites. So shown on the lower right, these are some of the students who were instrumental in terms of building this museum exhibit. The way it works is you push this button, and as you push the button, water starts to flow through a cave. And on the back side of it, we have an entirely different cave passage, but water flows through the system. On the very top, it looks like this. We had fun with Lego figurines. And what we're trying to do is illustrate that people camping or flowing down the river, they're not honestly that far away from where there may be some cavities that exist in the subsurface. Also, in this museum exhibit, we have a raspberry shake seismometer in this back corner, which you can also see right here. So this is now in our museum at Wheaton College. And so again, if you're ever close by, come to our museum and you can check this out as well. But basically, this seismometer is continuously recording the responses that occur as this water is moving through the cave passage. So I'm going to play a little video. This was put together by a student. He just completed it here recently. But this will illustrate, again, a little bit about our project, what we're trying to do, as well as you'll see some results from our museum exhibit. And again, the sound's coming across okay.
It's a little soft.
These are a few pictures from the field. That's showing our background seismic signal. And Ethan's pushing a button, it opens the ball valve, and now you can see the seismic signal that results as the water's flowing through the cave. So it's a little bigger than what the background signal was. Here the colors are a little bit brighter, a little bit more seismic power on that little image. So Ethan was shown at the end there jumping. He was instrumental in building this, and Donovan Michelle just created the video. So anyway, this is posted up on YouTube, and you can get access to it at my website. All right. So again, these instruments can record responses as water is flowing through caves, even in our little toy model. But it captures all sorts of things. You jump, any kind of environmental process, it's able to capture that kind of response. So now let's go to the second part of the talk. This is our site up in Minnesota, and this is the earth burps part of the talk. Here we captured some seismic signals, which we think are occurring as we get a compression of air pockets as water levels are rising in the caves. And then all of a sudden, once we release those compressed air pockets, we think they're generating enough energy that we're recording the seismic signals. So this project, this part of it was conducted in southeastern Minnesota. Here you can see there's a pool set up in this picture, this blue thing right back here. What happened is we filled this pool full of water, and then we dumped it into an overflow dry spring. In this picture, it's no longer dry. You can see that there's water that's actually flowing on the surface. But when we first started this, there was no water flowing along this channel. It was just emanating from this spring house. So the pool is on the map, which is indicated on the star. On this picture, I'm basically standing over here on the road and taking a picture looking to the south. But our pool is right here at the star. We dumped the pool out of, or we dumped the water out of the pool, and it ultimately went into an overflow spring. Early on, this overflow spring was completely dry, such that that water quickly entered a cave, which is indicated by the brown here. We were able to map out that cave that day, and it went here to this red square, which was a part where the cave was now completely full of water. It was a sump that existed in that passage, so we couldn't even explore any way further. But with some subsequent mapping, we were able to also determine that the cave map moved off in this orientation. So what happened is we dumped this pool into the overflow spring, and then the water probably moved along this cave passage, and then it probably found some other smaller passage and ultimately flowed to the spring. We had a bunch of sensors to monitor water level, discharge, also changes in some of the water quality parameters. And then we had a bunch of these circles, our seismometers, that we set up above our inferred path of the water in the subsurface in order to record the seismic response that occurred as the water was moving through the system. So shown here, I'm going to show you one of our pool pores. So this is our second pool pour. In a minute, I'm going to talk about that time right when the water first hit the rock. And so we're just dumping this large slug of water. And again, we wanted to record the seismic response that occurred as this water moved through the subsurface. And in this particular pour, we emptied that entire pool in a minute and a half. But I'm going to speed ahead here a little bit. We see here we're getting near the end. Speed up a little bit further. And then finally, we pull up the side, and the last of the water comes into the system. So then at this point, we tried to be quiet such that we're not generating seismic noise. And here is one of our instruments right here, and it's recording the seismic response as this water is moving through the subsurface. And so shown here are some records of what happened. This was just a short little campaign. We set up instruments for a few days, and then we did a couple of experiments over the course of 2 days. So it's not a whole lot of monitoring here. At the top, we're looking at the vertical component, whether we're getting vertical motion, and this is showing us our velocity seismogram. So we're looking at the ground level, how it's moving in a vertical orientation. Here you can see this is when we dumped the first pool, and then we were quiet and just tried to record the response as the water was moving through. After some time, we filled the pool full of water. We turned on a pump at the perennial spring and pumped it up to the pool such that we could dump it in to that overflow spring again. And here's our pool dump too. That's the video that I just showed you. And then again, we sat down, tried not to move, just record the seismic response. And then we turned the pool on again to fill it up for a third and final planned dump the following day. So then we went home. These are all in UTC times. So then we started to drive out to the field site, and it was pouring. There was a lot of rain. And we got out to the field site sometime right around then. And then we went into the barn at the site. And as we came back out, we saw that the overflow spring was actually started to flow. And right after that, we actually got the largest seismic signal that occurred during the study as the water levels were rising. When it became apparent that the water levels weren't going to decrease anytime soon, we simply dumped the pool on the surface. And in that case, it simply flowed across the surface rather than flowing through caves that existed in the subsurface. On the bottom, we're looking at the same time. This is what's called a vertical component spectrogram. What we're looking at here is seismic power across a range of frequencies as a function of time. And different kinds of environmental processes will cause unique responses. Here you can see when we had the pump on, when we were actively pumping water from the perennial spring up to the pool to fill it up, you can see that we're getting like these harmonic oscillations up here at these higher frequencies. So we can basically look at the seismic data and we know exactly when that pump was on in order to fill up the pool. And so what we're trying to do is find the unique characteristics that are associated with water that's moving through the subsurface so that we can make use of that information to characterize the conduits and other characteristics of the aquifer in the subsurface. So shown here are the responses that occurred during our second experiment. Here I'm looking at the 20 minutes that occurred from the time when we started to dump the pool into the overflow spring. And it only took us 90 seconds to dump that pool into the overflow spring. And you can see that most of our seismic responses basically occurred during that time. So again, this is just looking at the vertical velocity of the land surface. Here we're looking at our discharge. Even with that large slug of water, we couldn't change the discharge too much at the perennial spring. Maybe we increased by a little bit less than 5%, but we didn't cause a big change in terms of discharge of the water that was flowing out of the spring. Here we're seeing some sodium chloride and also a temperature. What this is recording at the spring is the actual water from the pool that is finally reaching the spring. In this case, we didn't add any sodium chloride to this pool, but we did to the previous one. So there was a little bit of residual salt. So it's picking that up along the flow path. And then the temperature, we filled this pool just minutes before we dumped it. So it didn't have time to increase in temperature, although you can see it was slightly elevated. But again, as we see this temperature perturbation, this is telling us the time when the water was actually reaching the spring. So it sinks into the overflow spring here, flows through the caves, and then eventually it starts to appear at the perennial spring downstream. Okay, but again, there wasn't many seismic signals here. It was mostly just when we were pouring the pool. So here I'm zooming into the first minute of this pool dump. And here we're looking at the vertical component seismograms from all stations. So this is just how the vertical velocity is changing through time. And then on the bottom, again, we're looking at the seismic power. But these green colors are higher power. The blue is lower power. So again, we have seismic power across a range of frequencies as a function of time. So we started to pour pool 2 here at time 0. And what happened is you can see here from like 8 to 13 seconds, we had signals that were slightly larger than the rest of the signals. It's even more clear here on the spectrogram. You can see here at the low frequencies, we've got a lot of green vertical bars here. And then at about 22 seconds after the start of the pool pour, here we also saw some larger signals. And you can see that at the higher frequencies, all of a sudden we have a new seismic signal that was recorded. So in the next couple of slides, I'm going to zoom in kind of to this data, but look at it in a slightly different way. So again, we're looking at the vertical component seismogram. We're looking at how ground velocity is changing at all 12 of our seismic stations. Some stations didn't record it at all, but some of them did record it. And the seismologist, Sue Billick here, she's filtered the data such that she's only looking at the signal between 1 and 8 hertz. She was also able to determine the direction of the source of the signal. Where did it actually come from? And she's also got the slowness, which is just the inverse of velocity. And what she found is the signal, we had the greatest power right here, kind of west-southwest. And right at the center here would be at the center of all of our seismic stations. So this location would be consistent at the location where the water was falling onto the rock as it started to move into the overflow spring. So that was the very first signal. And this time, like 8 to 13 seconds after we started to pour the pool, would be consistent with that as well. It took time for the water to flow on the grass before it fell as a waterfall onto the overflow spring. Here we're looking at more vertical component seismograms. Here Sue has filtered between 25 and 70 hertz. So this is the signal that was occurring about 22 seconds after we started to pour the pool. And if you look at the direction where this came from, it's generally south of the center of our network. So this would be more consistent with the location of the sump part of the cave passage. So again, water entered the overflow spring, it flowed through a dry passage, and then it hit this part of the cave where all of a sudden it's completely full of water. So it seems like we're getting a source of a signal that is originated right where that sump is located in the subsurface. Again, we filled up the pool. We were going to do one more experiment the next day and then pack everything up. But we had this massive rainstorm event. And shown up here, again, we're looking at the seismic signal. By far, the largest seismic signal that occurred is right here, which is just after our overflow spring started to flow. Again, we couldn't change discharge very much with our pool dumps, but here you can see this natural recharge event. We went from 100 liters per second. We had small increases. And then eventually there was a much larger increase. We got up to a discharge of about 300 liters per second. So we increased discharge from 1 to 300 liters. This next curve is simply showing us the slope. And as we look at the seismic signal, the slope of the discharge, we were certainly past that point, but this largest seismic signal still occurred as the water levels were rising in the conduit system. So water levels were still rising there. And then finally, whenever you have fresh rainwater run through a system, it hasn't had much time to dissolve away minerals. So you'll get a decrease in electrical conductivity. Here you can see the biggest decrease. So perhaps there's some smaller flow paths that is contributing flow to the spring here, and then a larger flow path. And similarly, it also caused changes in temperature. So these are changes that we recorded at the spring, but indicative of water moving through caves pretty quickly in the subsurface. So we're going to zoom into this seismic signal. Again, occurred as the water levels were increasing at the spring. So again, here, we're looking at this vertical component, this ground velocity in the vertical motion. And then again, we're looking at another spectrogram here. Again, power across range of frequencies as a function of time. Again, this by far was the biggest signal. It was orders of magnitude larger than what we had with our injection experiments initially. And you can see that it's producing a lot of power at some of these higher frequencies. I'm going to zoom in here between these two red lines, and that's the record that's shown here in the upper right. And then if I again zoom in between these red lines, that's what's shown here in the lower right. So you can see most of our power is generally above 30 hertz. That's where we're generating most of the power here from this signal. But you can see these different spikes that are coming through various kinds of events. So shown here, we're again looking at vertical component seismograms from all 12 seismic stations. And again, these are showing these really large signals. In this case, as we look at these signals aren't lasting very long, and they're repeating maybe every 0.3 seconds early on. From here to here is 5 seconds of time. So we had a lot of really large vertical velocity variations initially, but even later on, we continued to see some of these pulses that were recorded at these various seismic stations. So these signals were recorded at all 12 stations. And again, here we're specifically filtering the data between the 30 and 70 hertz, those higher frequency signals, which seem to be recording that. Again, as we look at the direction from all of those pulses that we were just observing, we see that there's no one location. Early on, the signals were originating from the northwest, and this is 0 degrees, 90, 180, 270, 360. So up here, we're in the northwest. And as time went on, our signals were more towards the south. Here you can see this yellow color. So this green and yellow were the biggest signals. So it seems like our signals originated from multiple different locations. At one point, they were originating from the northwest. At a later time, it was originating from the south. So from these pulses, we were also able to estimate how much energy would have been released in order to cause these seismic changes. And so what we did is we did some processing of the seismic data, and we don't know the source specifically, but what these red curves are illustrating is the amount of energy that would have been released in order to generate these seismic signals if the source would have been maybe 20 meters away, 40 meters away, or 60 meters away. So generally, as we look at each one of these pulses, we're generally causing anywhere from 1 to about 200 joules of energy in order to produce these signals. So if we summarize the kinds of things that we saw here during this study, we see that the largest signals occurred within a period of 5 seconds during that natural recharge event. Again, water levels were rising, but the overflow spring had already started to flow. Each of these events didn't last very long. Again, it looks like we're kind of getting some oscillatory behavior. We get a pulse maybe every 0.3 seconds. And then as we look at the location, it looks like they're originating from multiple different locations as we looked at the direction of the signal. And finally, we did some calculations that suggested that maybe there was about 1 to 200 joules of energy that was released with each one of those pulses. So as we start to think about the conduit and think about relevant processes, we were ultimately able to come up with 3 things. So on the top here, I'm just trying to illustrate a cross section. Here we have a flood wave that's coming into a flow path that already has some water. In the lower part, I'm trying to illustrate different kinds of processes with these numbers. Every place where I have a number 1, I'm trying to illustrate a place where we could get a burp from the earth. So places where we're going to compress air pockets as the water levels are rising, and perhaps we're releasing a bunch of energy as those air pockets are released. So in this case, this may have had some air initially, but as water levels start to rise, all of a sudden we're going to pressurize that air. Eventually, it might release via some sort of crack or some sort of ventilation pathway. The second process is maybe we had a flood wave that hit some sort of constriction. In this case, when this flood wave hits this wall, maybe as that water impacts that wall, that's able to generate a seismic signal. The third option is perhaps there was a rock that fell. Maybe we have a rock fall in the cave. And so as that rock falls, it generates energy that moves out in all directions from that source. All right, so those are the 3 relevant processes that we think perhaps could be possible for generating some of these signals in the cave. First of all, if we consider a rock fall, the potential energy of dropping a 100 kilogram rock 1 meter, that would produce a potential energy of 980 joules. And the potential energy is the mass of that material times the gravitational acceleration times the height that it would fall. There's been a lot of work of seismologists looking at the seismic signal that's associated with rock falls, and they've developed this relationship, which is a function of this potential energy. But basically, if I do that estimate from our work, I see that this would produce 4.3 times 10 to the minus 4 joules, or 0.00043 joules of energy. And again, from our energy estimates, we were expecting something like 1 to 200 joules of energy. So in this case, it doesn't seem likely because our energy is a lot greater than this energy. Also in these papers, the rockfall signature occurs at much lower frequencies. And then the fact that we have sources originating from multiple locations, it's possible that we could have a rockfall, but it's probably highly unlikely that we had a rockfall falling from the northwest cavity passage and one from the south as well. So all of those factors seem to suggest that it's probably not a rock fall. However, it's very common, even if we think of sewer systems or water line distribution systems in communities, they often have these pressure transients that resolve as air gets compressed in some of these pockets and some of these pipes through below communities. And in fact, on the left, here's a picture. This is a manhole that is being blown off because of water and air that's ultimately coming out of this passage. So there was too much water that got into this stormwater tunnel during a storm event, and all of a sudden you get this pretty, you can look online and see videos of this process of these just venting when you get these big storm events and when you get air pockets that are trapped. On the right, we're looking at a little simple model that someone ran. Here we have a reservoir where the water level is up at this level, indicated by the upside down triangle. And then they have a little passage here, and they open the valve, and there's an air pocket in the upper right. And what happens is they're looking at how pressure changes as they open that valve. And ultimately, the kind of signal that develops depends on what's the volume of your air pocket initially. But anyway, we think that this is potentially likely that we're actually capturing the release of some of these air pockets in the subsurface. And so what we did is we did some basic, we did some calculations to try to get some estimate. So again, water levels are rising, we're compressing the air. Eventually, maybe that air encounters some sort of fracture and it can release up to the Earth's surface. And as that air pocket is released, that's going to release some energy. So we did some calculations. Here, if we were to increase water levels by 1 meter, and in this particular study, for our overflow spring to start flowing, it had to increase by 3 meters, so probably a couple times even larger than this. And so if we have water levels that are increasing by 1 meter, in this case, the star is indicating the location. If we had an air pocket that was 15 liters in volume, under those conditions, if we compress that air pocket, and then if it releases up to the atmosphere, we could perhaps generate 100 joules of energy. So this is showing you the kinds of the conditions that could produce the kinds of energies that we were able to generate from our signals. So if water levels would have increased anywhere from 0.3 meters up to 3 meters, and then here we're looking at volume of the air pocket of 0.05 liters up to about 50 liters of air, those are the conditions that would produce the 1 up to 100 joules of energy, something similar to what we saw at the study. So because of these energy calculations, we think that this is perhaps a likely source of the generation of those signals. So, and it seems likely as water levels are rising, there's going to be places in the conduit where we're going to compress some air. Some of those air pockets could be released. Some of them may move along the flow path. And once it intersects some sort of fracture, then it can be released. And so as that air pocket is compressed and then released, it perhaps releases all of this energy. I still need to somehow figure out how to do a calculation of how much energy would be associated with the water hitting a constriction in the cave. But I don't think that's a very likely process in general in karst systems. So I think that it's this earth burping is the most likely explanation for why we're actually seeing these seismic signals in that case. All right, finally, and we're going to spend less time on this, but we're going to go down to our site in Florida. And now as water levels are rising and falling, we're basically going to look, can we actually see the Earth's surface tilting as water levels are rising and falling in the subsurface? So our field site in Florida is in north central Florida. It's at Olino and River Rise Preserve State Parks. There, the Santa Fe River flows across the surface right along my mouse here. And then once it gets to River Sink, which is this location, the entire river disappears underground. All of this water from this massive river flows through these caves, which are indicated in the red lines. They've been mapped by cave divers. They're always completely full of water. They are 20 meters in diameter, about 30 meters below the surface. Sometimes they rise back up to the Earth's surface. So it's like a spring on one side, and then it's a sinkhole on the other. This is called a karst window. It just looks like a little pond or a lake, but it's connected to caves on both sides. And so it flows through a series of caves, and eventually the water reemerges at River Rise, where this massive river just appears from underground. So you can walk up and all of a sudden you see this river that appears out of nowhere. It's this water that comes up out of the caves. At this site, we were monitoring for water level changes and other parameters at all of these little blue circles that are indicated on the map. And then with the various triangles, we have seismometers, or else we also had tilt meters, which are capable of recording how the land surface tilts through time. And so again, our goal, can we make use of various kinds of geophysical data sets, how the land surface is moving as water levels are rising and falling the subsurface, as water is flowing through the caves? Can we use a record of that deformation at the land surface in order to map out where some of these cavities exist in the subsurface? So shown here is Sue and Jacob. They're right near one of our instruments. The seismometer is buried just off of this picture, but we kept all of our instrumentation in these boxes to try to keep everything dry. So they're at a seismic station. In the upper right there, you can see Lauren. She's at another seismic station. In this case, we deployed 14 seismometers for a 3-year period of time. We also deployed 150 of these smaller seismometers in the upper right corner that were deployed for just a 1-month period of time. We were trying to capture a large recharge event that would occur with a hurricane, but after we deployed the 150 instruments, we had like almost no rain for the next month. So we didn't really see water levels rise at all. However, water levels were high, and so we saw a pretty good waterfall during that entire experiment. So we still were able to collect some pretty good data. In the middle here, we have a borehole that was drilled by the Florida Geological Survey, and we installed a tilt meter that was about 20 feet down below the surface. And then shown here is Tatiana. She's doing a hand measurement at one of our PVC pipes that went down into the surface water body. Ricardo here is doing some hand measurements on a well at the field site. John is shown here at our weather station. And then in the lower right, here we're performing a hammer survey. So after we had all the hammers set up, we did these hammer surveys where we hit a sledgehammer on a piece of metal, and we're basically looking at the response at all the seismometers in order to characterize the subsurface as well. So I'm just going to show you a little bit of this project. There's a lot of stuff that we're still working on, so there'll be more to present, I guess, at a future meeting at some point. But our question is, can we actually use these tilt meters, which is shown right here? Again, this was dropped 20 feet down below in this dry well. It was just down the sediment. We put it down 20 feet below the surface to try to get rid of temperature variations at the land surface, because that allows us to track this tilting of the land surface a whole lot better. So as our initial trying to see if these could actually work, we did some modeling exercises. And shown here, we're trying to simplify the field site. Here we have our conduit that has a 10-meter radius or 20 meters in diameter that is 30 meters below the surface. And what we did is we tried to add some water that is recharging the aquifer from the conduit. So what happens during storm events, water flows on the Santa Fe River, and then it sinks in River Sink. And then water starts to move out from the caves into the rock that surrounds the conduit. So we're trying to simulate recharge as we're adding water here at the conduit wall as the water flows into the aquifer. And so I'm going to show you 6 different examples. We're looking at confined and unconfined aquifer systems, and then we're looking at Paleozoic to Cenozoic limestone. And the main takeaway here is under these different aquifer systems, they're going to have different properties which allow that water to propagate further away from the conduit. So I'll show that here on this slide. Here we're looking at the 6 different scenarios, confined and unconfined system. And then we're looking at the young rocks, the intermediate age rocks, and the older rocks. And so as rocks become older, especially limestones, they initially have a lot of porosity and permeability. It's really easy for water to flow through. However, with geologic time, that material becomes more deeply buried. So there's compaction that occurs. There's also recrystallization. And the net effect is you start to make the holes in the rock smaller, and they're not as well connected. So it's more difficult for water to actually flow through the aquifer system. So in this case, for these 6 different aquifer systems, we're seeing that with the confined Cenozoic aquifer system, as we increase water level, that's able to propagate throughout the entire aquifer system. The red colors illustrate the most significant increase in hydraulic head, or we can simply think of increase in water levels. Whereas down with the unconfined Paleozoic, we don't see much of a change in water levels at all. Okay, so we're increasing the water level with all of these colors that are not blue. The red ones were increasing water level the most significant. On this next slide, we're still looking at the 6 same systems, but we're looking at how the vertical land surface is raised up as the water starts to move into the aquifer. And these are really small. We're looking at vertical displacement in micrometers. A micrometer is 10 to the -6, so 0.000001 meter is 1 micrometer. And in this case, in the upper left, where we had water that was recharging a lot of the aquifer, you can see directly above the conduit, we're getting 50 micrometers of displacement. Here's a contour line where we have 45 micrometers of displacement, 40, 35. In these other cases, we didn't cause as much vertical displacement above those systems. In the cases where they're blue, there's very little vertical displacement that's occurring. So what happens is, again, we're going 50, 45, 40, we start to cause some tilt that occurs away from the conduit. And in this next map, we're basically looking at the tilt of this signal. So in this upper part, what happens is the displacement right above the conduit, again, it was most significant displacement right above the conduit. And so we get this tilt signal as it starts to tilt away. So all of these blue colors, all the blue colors correspond to the land surface that's tilting away from the conduit. And then down in the red colors here, it's actually tilting towards the conduit. So what happens is as we start to raise water levels in the caves, it causes the land surface to go up, and below it goes like that. So we pressurize the conduits with more water, it balloons out, and then as that water level falls, it comes back down. And so these instruments, we can actually capture how the land surface is moving. So if we're monitoring, that's not what I meant to do. If we're monitoring at the land surface, we can basically try to capture these kinds of tilt signals. So this suggests that if we have these tilt meters and see these various kinds of tilt signals, we may start to infer what kinds of characteristics of a conduit or a cave would exist below the surface in order to cause that much tilt of the land surface. So I'm just going to show you two quick things here with the data, and then I'll close it out here. So on this figure, we're basically looking at the model input, which is shown in the blue curve. And so what I'm doing is I'm using water levels that we collected at one of our sites out in the field. And this is connected to a cave. And then I'm looking at the water that was recorded in a well not too far away from that cave. And so in our model, we changed some of the aquifer parameters in order so that we could reproduce the water level changes that existed in our model. So in this yellow or orange color here, you can see we're generally reproducing the red. On the bottom, we're basically doing the same thing. We're just looking at a well that's a little further away from the conduit. So again, we adjusted the parameters of the aquifer such that we're getting the same water level variations from the conduit all the way over to the well. Now on this next one, I'm going to show you the tilt signals. So from our model, we can also look at how much tilt would have occurred with that signal. And that's indicated in this dotted line, this yellow or orange color. And then also from 3 of our different tilt meter stations, we're recording both the radial and the transverse tilt. In reality, if the field site was as simple as our model, we should have only had tilt in one orientation, the other would have been 0. But here you can see that we're getting tilt in both directions, both parallel and perpendicular to the conduit. Furthermore, as you look at the tilt, sometimes you get positive numbers and sometimes you get negative numbers. So it's going up and then later times it's tilting the other way. So in this case, this tells us that the field site is a lot more complex. Perhaps there's a number of conduits where we're getting recharge where it's tilting away from those conduits. So early on it's tilting in this direction, but later on, maybe there's another conduit over here, which is tilting in this direction. So this is really complex. Another thing is right now, the tilts that we're measuring in the field are quite a bit larger. Here we have microradians, over here we have nanoradians. So we need to do a double check and make sure we don't have some sort of unit conversion error somewhere. But it turns out that this is really complex. We've learned some important things from these simulations, but now we're going to try to learn even more things by making our models more complex to try to better be able to reproduce some of these signals that we see in the field. So in conclusion, these seismometers seem like they are capable of recording earth burps. Basically, again, water levels are rising, we're compressing air pockets, and then those air pockets may see some sort of fracture and may release up into the atmosphere. And both the multiple locations where these are originated from, as well as our calculations, the 1 to 200 joules of energy are pretty similar to what we saw at the field site. So because these signals are originating from the conduits, that perhaps suggests that we can actually map out where the caves, the source of these signals, exists in the subsurface. And then with the tilt meters, we can see that with the models, we are generally seeing these tilt that is occurring away from these pressurized conduits at the surface. So perhaps we can use a record of this tilt as a way to infer some of the characteristics of the conduits that exist in the subsurface. Granted, with the little bit of data that we've compared to in the field so far, it's really complex. So there's still certainly a lot of work to do, but it seems like geophysical tools are pretty helpful instruments as a way to characterize these karst aquifer systems. So thank you so much for your time and attention, and I'd be happy to try to answer any questions that any of you have.
That's a lot. Wow. I'm going to start with some questions. The Mendenhall Glacier, I lived in Alaska for many years, and you can hear the glaciers move. And I know that there are individuals that will hunt oysters underneath the ice flows, the ice sheets, and the really experienced ones, they hear the sounds with the tidal waves coming in, and they follow that. Is that pretty much the same premise as the waves that you're measuring?
Yeah. In fact, karst or glaciers are really similar. A lot of times you can develop ice caves in glacier systems. And at the base of glaciers, when they're melting, you get water that's flowing in the subsurface. So there's a lot of signals that are arising from a number of processes, including just as the ice is flowing, it can crack and create a crevasse. And in that case, it can generate some seismic signals. As the water is flowing through the base of the glacier, that can create some seismic signals as well. So it was actually the work in the glaciers that initially made me think, well, we should do this in karst aquifer systems. Water, there's a lot of water that flows through these caves that in Florida are 20 meters in diameter. So that's a lot of water. So it was honestly seeing what they were starting to observe at the base of glaciers that made me think, oh, maybe this will be a really useful tool to look at these karst aquifer systems as well. But people are using seismometers to learn about a variety of different kinds of environmental processes. Again, historically, these were used to identify where an earthquake occurred, so we're just monitoring earthquake responses. We're also making use of that data to try to characterize the structure of the internal earth. Actually, seismic waves are incredibly important in terms of us understanding our big picture of what the subsurface of the earth looks like. In terms of us drilling, we've barely scratched the surface of the planet. But outside of those historical uses, people are using these to learn things about processes that occur in glaciers, in other kinds of aquifer systems, looking at coastal environments, learn about mass movements, look at how much sediment is moving down streams. So there's a variety of different kinds of environmental processes that we're learning some pretty cool things.
Yeah, that's very cool. I'll let somebody else go next.
As a question, can you use this sort of thing to predict where there's going to be a potential sinkhole occur, how big that sinkhole will be, and that sort of thing?
Yeah, so even though we've been working on this for a few years yet, there's still a lot more work to do. But with some of these signals, as they are originating from the cavities, ideally we would be able to start to map out where some of these caves exist in the subsurface. So I think it's going to be difficult to think about the size of these passages, but also I guess when we're trying to characterize just the structure of the system and try to do some of the things that we were looking at with the tectonic plate that is subducting below Tonga. In that case, maybe we'll start to be able to get some sort of estimate for what exists in the subsurface. And then certainly one of the potential things that results from this work is we can create hazard maps. Which areas are potentially susceptible to sinkhole collapse? If you have a big cavity that exists in the subsurface, then you could potentially have a sinkhole that occurs in that region. So if we're able to identify where the caves exist in the subsurface, we can maybe say something about locations that are more likely or less likely to experience a sinkhole in the future.
Florida has a lot of limestone and a lot of sinkholes that create major problems. Is there any way to use that to help finance your type of research?
Possibly. At this point, it's primarily just been a research question. Again, we're still working through the data. If we could make some really good results, I think some people might even be more interested in some of our results, but we've got a lot of work yet to do before we kind of show some of the capability. We're just trying to understand what kinds of signals are being produced and then think about how we can use it. But some of our initial motivation was thinking, can we actually monitor for water levels in the subsurface? Can we map out these cavities? That's relevant to sinkhole hazards, where sinkholes are likely to occur in the future. But every once in a while in the news, you hear there was a house that was swallowed down in Florida or other places. Florida is certainly a common place where this happens.
So do you have theories that based on the level of tilt would also indicate if it's going, if there's a large level of tilt, that could also indicate that at some point it is going, since it is so elastic, if you would, that it will could also predict a sinkhole because of the,
Yeah. No, I think you would be able to observe something before it happens. The challenge is having the instrument there to observe it. It would be awesome if someone would set up an instrument right near a place where a sinkhole develops in the future and see the response. Yeah, and these motions aren't large. Again, we're talking about micrometers of displacement at the land surface. And again, a micrometer is 1 micrometer is 0.000001 meters. So the land surface isn't moving very much. But I'm pretty sure you'd probably see a pretty unique signature before that fails. I have no idea how much warning you would be able to provide. Yeah. But it's one of the challenges, like even we're trying to develop these early warning systems in terms of where earthquakes occur. This would be another example of that. It's really hard to do it, but there's a lot of people who are working towards trying to create some sort of early warning systems. Yeah.
Is there a correlation between the number and the size of the hurricanes and the number and size of the sinkholes? If you had a lot of energy from a high weather system, you would expect the sinkholes to be blown in a much more common way.
Yeah. Generally, a lot of the big sinkholes that open up, a lot of them follow really massive rainstorm events. In fact, the example that I showed in Minnesota, that was like a 100-year flood event that occurred in Minnesota, and it opened up that new sinkhole. So I guess I'm not aware of a study specifically, but it would not surprise me at all to see that you're getting larger sinkholes that develop with larger, more massive storms as well.
well, it would make sense because if the tilt is causing it with all the mass influx of water, causing it to tilt, and then when that water starts, draining away, you've created instability.
Yeah. Well, in some cases too, just the sealing of a cave passage, as you dump a bunch of water on it, all of a sudden that's a lot more load. And so now that fails and you get collapse of that cave sealing, collapse of the surface down into the passage.
So I have another question. One of your pictures you showed where the water from the sink rise and the river sink, where it disappeared and then where it surfaced again.
Yep.
And in both of those pictures, the water was absolutely smooth. There was no sign of movement that, for a river. Is that typical, or was that just happened to be those days those pictures were taken?
Yeah, I think it's more those days the pictures were taken. If you look closely, you can see the water's flowing. And the little video that we had at the start of the interactive museum exhibit, in one case, you can see that there's some water kind of swirling at river sink. There's like some algae in the stream, and you can see that there's a little bit of a swirl as the water's going down.
Okay, because it's like there was not even a ripple, and I was like, wow.
Yeah. No, it's still flowing there. Sometimes some of the karst windows, it simply looks like a pond or a lake, but water is still flowing there too. It's coming up at one side, flowing on the surface, and then it goes down the other side back into the caves. So I'm guessing many people are at that site and they don't even realize that there's caves nearby. They just think, oh, this is just a lake here. At the
Are the
surface.
water levels at those sites fluctuate? Do the water levels fluctuate a lot at a site like that?
Yeah, over our 3 years of monitoring, water levels have varied by like 3 meters.
Okay. Yeah.
So something on the order of 10 feet over that 3-year period of time.
Yeah.
They change quite a bit.
So you were probably very close to the Harmony, Minnesota caves? The
Yes.
caves? Yeah, and I went in those, and it's amazing how you don't even realize how deep those caves are until you start going down there.
Yeah.
And they're really extensive.
Yeah. Yeah. There's a cave, let me see, what's it called? I think a Minnesota Cave Conservation Foundation. And there's primarily one person in particular who has funded drilling some boreholes. And so you drop down ladders to get into the caves, and you'll often drop down ladders that are 80 feet or so to get down into them. But then these cave passages go on for a while. So again, you're at the surface. You may not necessarily know there's caves below your feet, but there can be a pretty extensive cave network.
So
And
I
again,
have
new sinkholes open, people drop down and they map out more caves. There's even more down there. So.
on the conduct tilting, because they're moving through different depths and different ages of rocks. For example, I know in the Harmony caves, there's a 100-foot waterfall. Could those waterfalls and the change be what's accounting for the pulses that you were seeing? Because could the pulses be because of twists and turns and waterfalls?
Yeah, I think the waterfalls would be a great candidate, because all of a sudden, in that case, you've got water falling a long ways, and then it's impacting the rock on the floor. So that's going to generate a lot of energy. So right where that waterfall hits the floor, it's going to be a source of some of these seismic signals.
So
Honestly,
did you map the where, I mean, could you throw in some kind of GPS marker in with your pool water to see where it goes and if it changes in elevation?
Well, you can't do GPS because that is dependent on having access to the satellites at the surface. But cavers will go down in caves and they can send out some radio signals where they're able to figure out where they're located at. But then they go down and they're mapping. They make use of various kinds of technology. In the past, they used just a tape. They did a basic tape survey. Nowadays, there's some laser instruments they can make use of to map out caves a little bit faster. Like a lot of states, it's becoming more and more common to have LiDAR data available, which we can use to get high resolution topography of the land surface. But there's LiDAR instruments, well, even some cell phones now have LiDAR in them. But you can also get these little LiDAR instruments where you can take into a cave and you can get a pretty good 3D model of what that cave would look like. So from the LiDAR data, you're basically able to create these point clouds, and all of a sudden you can see what the cave system would look like. But yeah, there's been some people who have worked on basically creating some robots that go through cave systems, and if they're capable of mapping stuff. They've had some success. I haven't followed them too closely to see where they're at with that. But if you want a really good map, you'll have a human down in there as well, which requires a large enough passage such that the human can actually enter. In these cases, there's probably a lot of passages that are too small for us to enter that are really important in terms of water flow through the aquifer.
No. I'm sure other people have questions. I don't want to keep asking. All right, so, okay, I've got one for you. When I was going through the Harmony caves with my kids years ago, they were talking about, you know, there's a strange phenomenon after it rains, or when the rain's coming, then there's ghosts in the caves and they can hear it. So could that be also they're hearing the air being displaced because of water movements, and that's what generates all those urban legends and superstitions about, you know, the caves being haunted?
Yeah, for sure. Caves are dynamic systems. And if you get a big rainstorm, in fact, they'll sometimes shut down tours at different places. Just as a big rainstorm, water levels are rising, that's changing the dynamics of how air moves through the system, of how water moves through the system. Yeah, I wouldn't be a bit surprised if that's how some urban legends are started, just as the dynamics are changing as water levels are rising in the system. Yeah.
And have you found any evidence of the burps where they've actually emerged at the surface? Where the pressure has been enough, you know?
Yeah, we did this experiment, and as we've thought about what are the sources of these signals, we've thought that the earth burp is the best explanation at this point. But honestly, it's so early in this work, we'd have to do more monitoring to see, do we actually see evidence of this at the surface? At this point, we think it's the most likely explanation, but it would need to be confirmed with some additional work. Yeah,
Yeah,
perhaps we
I
could
would-
even
I
set
would
up
think-
some.
Yeah, I would think if there was a lot, if there was a real dry cave and then an influx of water, like I'm thinking of the cave in Thailand where the young men were,
Soccer team.
yes, and so there had to have been several burps as the caves, were filled with water and I'm just wondering if there's any surface evidence created from the air pressure releasing.
We haven't really looked yet. Time will tell if we can actually see that at this. But yeah, the case that you brought up in Thailand, that was a tragic story. A soccer team went into a cave and it was the monsoon season. They were getting a lot of rain. So water levels were rising. The team went back into a cave passage. And while they were back there, the water levels rose so much that they could no longer get out. So that's why they were stuck there.
It's an amazing documentary on that, but I'm just wondering that, where did that displaced air? Because you're talking a lot in that huge cave system.
Well, in
How
some cases, there may be some pretty sized conduits where we're not really pressurizing the air. Maybe that air is able to be released pretty easily. But in other cases, if there's not the conduits, then you're going to pressurize it. Eventually, the pressure might get so much that it will push it through a tighter fracture and release.
Mhm.
But yeah, again, we think this is the process, but there's more work that would need to be done. Can we actually capture this at
So
the?
you could be feeding a whole bunch of different theories and everything else with the burps and a whole new study.
Yeah.
You're gonna come up with a better name than earth burping.
I thought that might make some people interested in actually listening.
Yeah.
Yeah, well, trust me on that. When you start looking up, Googling earth burping,
Yeah. I guess I haven't tried it
just
yet.
trust me, I'm not gonna do that one.
Okay, I should have tried that before I named it, I guess.
Do you have actual pressure measurements of the gas pressure down there? When
We
you have
don't. We don't, and that would be another thing to do, to go and instrument a site that we know fills up during these storm events and monitor how does pressure change in some of these cavities. But yeah, this was, I wasn't even thinking of this process when we first did this experiment. I was thinking, let's put some seismometers and we'll see if we can detect some kind of signal that's relevant that's generated from the water flowing through the passages. But I wasn't thinking of all the stuff in the subsurface. But you raise a really great point. It would be awesome to have an instrument down there and kind of track how is the pressure changing in some of these cavities as water levels are rising in the system. I wish we had that data.
it could be sizable in some areas,
Yeah,
You think so, yeah.
particularly if you had a dome that was somewhat sealed, so the
Yeah.
gas actually was trapped.
right.
Cold water cave in northeast Iowa.
Yeah,
What do you find in that? I mean, we've had a pretty good presentation on that from Ray Anderson that used to be with the geological here in Iowa and stuff, and he's done a nice program on that. And I just was wondering what you found in that particular, or if you've done any instrumentation on that.
I have not done any instrumentation in that one. I know a little bit, but there's so little that I know about that cave. I think it's generally a bigger cave than some of the ones that we find in Minnesota.
It is.
And in terms of, I think that one is maybe like 200 feet below the surface.
I think so.
Or maybe it's not quite that deep. It's definitely deeper. Some of the ladders that I used to drop down to drop in caves in Minnesota were like 80 feet. And that one's certainly over 100, maybe it's 120. I can't
Yeah,
remember.
somewhere around that, I think, yeah.
Yeah, I think it's probably a little bit more of an impressive cave system just right across the border there in Iowa. But honestly, I don't know enough about that site. Are you
The
from
area,
Iowa?
oh, go ahead.
I was just asking, are you from Iowa?
Yeah, Cedar Rapids.
Cedar Rapids area, okay.
One of the things that is kind of unique about the Luhmann cave is there's for fossil lovers, there's places in there where you can see
Crinoids and stuff in there.
On the walls.
or
Your speaker's going in and out, Marvin.
I heard you sharing about that. You can find some crinoids in there.
Still not there.
Yeah. So the area that you showed on the map that had a lot of the, it was all blue.
Yeah,
w- So that whole area is, yeah, I'll wait till you get there.
yeah, I'll pull it up. So this is a map that was put together by a
Yeah.
doctor from the United States Geological Survey.
So that area that's all blue, I mean, are you saying that that whole area is just land over a whole bunch of water, underwater rivers and lakes and?
Yeah, and there are some areas that are more developed than others, but Missouri, there's a lot of sinkholes and caves and springs in Missouri. And part of that reason is because it's on the eastern US, so there's more precipitation, but then also you have a lot of limestone and dolostone that is right near the Earth's surface. It's not covered by sediments. On this map, the gray colors are kind of showing the humid eastern parts of the US, and then you can get a lot more precipitation up in the mountains. But most of the western US is pretty arid. There's less precipitation. And then also here, this pink line is showing the extent of the glacial deposits from the last glacial maximum. Or just from Pleistocene ice. So as glaciers covered the landscape, that's why in Illinois, especially here, there's some carbonate rocks, but they're more deeply buried. So as the glaciers flowed across the surface, they deposited a bunch of sediment. So we have the right kinds of rocks, but they're far below the Earth's surface. So the bright blue colors are regions where we have this carbonate rock that's either at or very close to the Earth's surface. As we look at these other colors that are kind of more greenish in color, here we're looking at carbonate rocks that are buried beneath less than 50 feet of glacially derived insoluble sediments, or this color. In this case, we're looking at carbonate rock that's more than 50 feet below some of these sediments. So anyway, all the colors correspond to the rocks that will generally form these karst systems, but you're going to get the most development of karst features if that carbonate rock is close to the surface. So there's more development here, and then you get some. I was doing a lot of work before in southeastern Minnesota, but even in Iowa and Coldwater Cave, as was just mentioned by Marvin, and southwestern Wisconsin, you have some karst development. We do have a little bit in northwest Illinois as well. Although as you go down to like St. Louis area, you can see some really massive sinkholes because you're right on the edge of some pretty significant carbonates there. And then all of Florida has karst landscapes, or it has carbonate rock, right? Yeah, you see a lot of limestone in Florida. And so that's why you see a lot of sinkhole collapses and a lot of pretty massive springs as well.
So are there other countries that are very similar that are experience the same number of sinkholes and?
Yeah, there are different regions. You can see,
Regions?
yeah, just comparison to the rest of the world. You can see we do have quite a few karst landscapes in the US. Europe has quite a bit of karst, especially when we talk about like southern China. There can be a lot of karst there that exists as well. And then there's other areas that have less, but yeah.
Have you ever done, and I'm just throwing this out here because I know we always talk about, how the fossils and all that, and I'm just curious if we went back in time, how that would look, and then how it's split apart, because it's, I'm just trying to think of like, when they were one landmass.
Oh, yeah.
You know what I'm thinking is,
Like Pangea.
yeah,
Talking about Pangea when they were all together. Limestone, it's the rock where you find a lot of fossils.
yeah,
So yeah. So generally, well, one way to form limestone is you just have a bunch of sea organisms, and once they die, their shells fall down to the bottom of the ocean floor. And then that material can eventually become a limestone. Early on, it has a lot of porosity and permeability, and you can a lot of times see the fossils really well. But in places like where I was working in Minnesota, it's older Paleozoic limestone. So it's had a long geologic history. We're generally talking about ages of like 300 to 500 million years ago. And so what happens is with that significant geologic time, that limestone becomes more and more deeply buried. It has other sediments on top. And so all of the shells and the other carbonate material, it becomes compacted, it's compressed more significantly closer together. There's also recrystallization, so it will dissolve in some parts and precipitate in other parts. And so the net effect is as you recrystallize the whole material, a lot of times you may lose any evidence of the shells that were once there as the rock gets older. So yeah, you don't have as good of preservation, although sometimes you can still find some great fossils in old carbonate rock as well.
yeah. Where you were conducting your research up there is I found some incredible fossils up in along that area.
Yeah.
One of the things,
I just mentioned, I had a farm up in northeast Iowa, the northwest of Decatur, which is a lot of karst sinkholes up there. And on the farm, we had two sinkholes that lined up with a spring that came out of the rock bluff.
Mhm.
And those three things lined up, the two sinkholes lined up with the spring. They're probably about 40 feet down, something 30 to 40. Is that something like that be a good candidate for this testing, or?
Yeah, I think we'd find interesting things at any karst landscape. There's always interesting things to learn. But yeah, sinkholes and springs. Again, if you get a spring larger than some little seep where water's just dribbling out the base of a hill or something, you get a significant amount of water, that suggests that you have to have some sort of conduit upstream
Right.
for that water to move that quickly. So it's possible you could get some of these processes as the water's flowing through the subsurface. Again, you're getting water flowing through these channels, and from those flow processes that could serve as sources of signals as water's hitting walls, or as you're compressing air pockets and that's released, or if you have a waterfall in places like Niagara Cave. I think all those would be relevant processes.
At this point, I'm going to stop recording, but if you have more questions, please don't be afraid to ask.